This is a series of lectures on magnetic resonance imaging. We will use the guitar as a teaching tool. Learning MRI by equations can be quite tedious. Here, for example, is an equation that describes the signal that is captured by an MRI scanner as a function of the magnetization in tissue, M. In fact, the data acquired loads up what is called Fourier space or frequency space. So this is quite complicated, and for an introductory lecture we have decided not to use too many equations. Instead, we will learn by analogy. This is not new to medical imaging. We think of ultrasonography as echoes, for example, of this child prenatally imaged. You see the face, you see the arm, you see the fingers here. We think of X-radiography and also CT scanning as shadows produced by X-rays that either transmit through or are stopped by the tissues in the body. The best analogy for MRI is actually music, and that's what we will exploit in this lecture. There are actually 3 lectures so that each one can be viewed independently and would require approximately 1 hour of viewing. Part 1 is on the physics of the guitar. Part 2 is on the components of an MRI scanner, and Part 3 deals with the image reconstruction process. So, first the physics of the guitar, then the components of MR, and finally an image is produced. So let's begin with part 1 that deals with the physics of the guitar. We will deal with sound waves, the parts of the guitar, the physics of a vibrating string. So in effect, you'll get a free guitar lesson out of this particular section. We'll talk about standing waves and harmonics. We will talk about frequency analysis or Fourier transforms. We will talk about the 3 ways that the frequency of a string is controlled on a guitar by changing the string type, the tension on the string, or the length of the string. Sound waves are essentially a series of high density and low density regions in air. So when a speaker is initiated, you can see that a wave is produced that has high pressure and low pressure. This velocity shows the speed of sound in air at approximately 340 meters per second. We hear frequencies of these sine waves in the range of 20 Hz to approximately 20 kHz. The wavelengths are shown here. Let's look at the basic parts of a guitar, an electric guitar. First, we have the bridge where the strings are attached, or the strings sometimes just go over another piece of metal or wood where all the strings are then set to their normal start position. We then have the nut, which is the other extreme of the strings. We then have frets, which are these metallic small bars here that allow the vibrating portion of the string to be selected by the player. We then have the tuners shown here, and these allow changes in tension of each of the strings. Here we have the pickups. These are the electronic components of an electric guitar, and the pickups are also sometimes controlled through a switch that enables the front or back pickup or both to be played. Les Paul is a guitar as we know it, but it is also a person, and Les passed away a number of years ago, but he was still playing at the Iridium Club in New York until the ripe old age of 80 plus. So here's another guitar, but we'll go through how we produce sound. All sound starts with a vibration of a string on a guitar. That string vibration is picked up by the pickups, and the pickups are essentially bar magnets, and as the steel string oscillates up and down. This creates a current and is picked up then and transmitted into an amplifier. And then the amplifier puts out the signal by vibrating a speaker cone, and that produces the sound that is heard by the audience. While we're here, I thought I would point out this metallic bar here. It is called the whammy bar or the tremolo bar, and it allows the tension on all the strings to be simultaneously increased or decreased depending on a push or a pull of this tremolo bar. Let's go to vibrating string physics now. Pythagoras was a rock star, probably one of the first ones, and he had a monochord guitar shown here. And here's the bridge where the strings are overlapping, and he's attached this to a sound box, which is basically the sound box of the guitar, and the sound comes out from this end as it does from the guitar hole. He studied the vibration of these strings and the sound produced, and worked out much of the physics that occurs during that presentation of sound. A little bit more physics here. If we use a famous equation, F equals ma, we can find the forces that are exerted on a string that is plucked here in the y direction. And we can analyze F equals ma in terms of the net force on this little piece of string in both the y directions and also in the x directions along the string. This is the equation that relates the change or the change along the positions of the string and the acceleration here of that string as a function of time. A solution to this wave equation is well known, and it's a sinusoidal wave, a traveling wave, which changes as a function of either position or time. So position, if you stay in one place, you will feel a sinusoidal oscillation up and down. Or if you fix and take a picture of a wave, you fix the time, then you will see that wave changing as a function of position. So let's talk about traveling waves. They are fine, but in fact on the guitar we have standing waves or stationary waves instead, and they are produced because the waves reflect at two fixed points. That is what we talked about before, the bridge and the nut of the strings. A solution to standing waves looks a little bit more complicated than the previous one, and it shows a combination of sinusoidal patterns. Kn is the wave number, omega n is the angular frequency of the vibration. The everyday frequency of the vibration is shown here, and you can see that it depends on the tension on the string, the length of the string, and also the linear density of the string, or the number of grams per centimeter of the string. This is linear density, and it is not the traditional density per unit volume. Note that the solution has a little n in it, and in fact the solution exists for n equals 1, 2, 3, and so forth, integer numbers. For n equals to 1, the standing wave produced looks like this. It bounces up and down between the bridge and the nut of the guitar. N equals 2, we get this kind of sinusoidal pattern. N equals 3, and so on. You can see these nodes where there is no motion. So how does a standing wave form by the superposition of traveling waves? Well, essentially they occur because the waves bounce at the bridge and nut. So for example, here's an initial wave, and when it reaches the nut it bounces back with a reflection, and that reflection is out of phase compared to the incoming waves. So when they add up together, the positive and negatives cancel and we get a null wave. There is no wave at this moment in time. But if we wait a little bit longer, these two waves have moved and it is possible for them to overlap, for example, here and here. And the net result now is a standing wave with a negative lobe and a positive lobe. And similarly, if we wait a bit longer, we can develop overlap of these waves and a positive lobe followed by a negative lobe. So these waves bounce up and down and are shown in the next slide for what is called the first wave, or the fundamental wave, up and down, and the second wave here. And these work in opposite directions. So as this positive feature goes negative, the opposite happens on this side, much like on a teeter-totter. So right now, let's take a relaxation break, and we'll give you an interlude and try to name this tune. This will exercise the other side of your brain and give you a moment to catch up on your thinking. We've covered a lot of material, and you need to get your mind off it for a little bit. See if you can name that tune. Here we go. So think of Rolling Stones. I'll give you a few more seconds. All right, that was Satisfaction by the Rolling Stones. It's their signature tune. They start their concerts with that. Keith Richards has a good time starting it, and the whole crowd goes wild. So let's get back to some serious thinking. Frequency analysis and control of frequency. Jean-Baptiste Joseph Fourier was a famous mathematician and scientist, and he developed a technique that allows sorting of different frequencies on any audio signal as shown here. These signals can be decomposed into a set of sinusoidal waves added in a weighted fashion. This is similar to splitting white light into its color components, but it's done mathematically. If you take a note on the guitar, we're going to take the 5th string. We count strings from the bottom up. This string has a fundamental frequency, F1, of 110 Hertz. But if we record that signal, we find that it is not sinusoidal. In fact, there are kinks in the signal. And one might ask, why is that? By the way, this is Duke Ellington, a famous jazz composer and big band director, and he wrote a song called Take the A Train. I just changed it a little bit to Take the A Tone. So let's look at the A tone. Again, the kinks are shown here. If we take the Fourier spectrum, the Fourier transform, using a program called Audacity that I highly recommend to you if you want to analyze audio signals, then you will find that there's an amplitude plot on the y-axis and a frequency plot on the x-axis, and it shows you where the peaks are and at what frequency. So you can see the fundamental note is very loud and occurs at 110 Hertz as expected, but there are other peaks at 220, 330, etc., integer numbers that are also present, and these are called harmonics, and all of these waves coexist at the same time on the string when it is plucked and give rise to these kinks that we talked about. So multiple waves are now standing together on the guitar. The first harmonic, the second harmonic, and the others which I have not shown. The first harmonic, the wave bounces this way. The second harmonic, the wave is sinusoidal but changes its polarity. This comes down as this goes up. I highly recommend that you see another video that was produced by the American Association of Physics Teachers, produced by James Lincoln. Here's the link. You might want to jot this down. I'll give you a moment. So here we are, we're back to the guitar again. I'd like to point out a few positions again, the bridge, the nut, and this important location here at the 12th fret. If you count these bars, you will see there's 12 here, and that cuts the string basically in half. That's the location of the midpoint along the guitar neck. If we place a finger on the 12th fret, we suppressed this first harmonic, and what we will hear is the second harmonic. Now let's see if we can make this happen. The harmonics are sounds that are produced when you strike a string. And when you think you're only playing one string, for example, if I play this string, you sort of hear the main note or the main frequency. But in addition to that, there are multiple frequencies in integer amounts that also are sounded, but you don't hear them quite as loudly. So the first harmonic actually has a wavelength and frequency that's between this part of the guitar and this part of the guitar. So the entire string is basically wobbling up and down this way. That's your first frequency. That's the primary note that you hear. But there is another one which is oscillating between this point here, the nut, and the 12th fret, which marks the half distance to the string. And that one creates a sine wave that sort of goes like this and then comes back out and lands on this bridge. And that's the one I'm going to try to bring out without you hearing the main frequency. So let's see how this goes. I'll put my finger on the 12th fret. If I do that, I will suppress the first harmonic, which is the one that's bouncing up and down this way. So that one will be blocked. But the secondary one that goes through that point will not be blocked, and you will hear it. So let me give you the fundamental one, and now I'll block it, and you'll hear the harmonic, hopefully. So that one is double the pitch of the first one. It's an octave apart, but you definitely hear it, and you can do that with all the other strings. Now let's see if you understood this concept. Here are two Fourier spectra, A and B, and if you touch a string at the 12th fret at its mid-length and you pluck it, which spectrum will you observe? This one, A, or this one, B? I'll give you a moment to think about that. If you answered A, that is correct. You will see that the main frequency at 110 Hz has been suppressed by just touching the string, but all the other frequencies are visible as shown here. Let's talk about controlling the frequency of the string. This can be done in three ways: adjusting the tension of the string, changing the string type or changing its density, or changing the vibrating length. That's a little bit trickier. So let's start with the tension. That's easy. That can be changed by turning these knobs, which will tighten the string around the post. Tension is adjusted with these tuners at the upper end of the neck of the guitar. And a higher tension gives rise to a higher frequency, as was shown in the previous equations. So let me demonstrate that effect. I will detune the guitar, and then I'll gradually increase the tension, and you'll hear the frequency go up, and then I will stop when we're tuned. So here we go. Now we're getting close. And now we're tuned back to where it should be. So the tension is very important for setting the string. We can change the tension in another way as well. This is called bending a string. So for example, if I'm playing a note here, I can also change the frequency a little bit by bending it or pushing it hard, and that increases the tension just a little bit, and you'll hear it. So that's another way of doing it. On other guitars as well, you will have a whammy bar back here, and when you depress or pull on that whammy bar, you're actually releasing the tension or increasing the tension on the strings. The reason I raise this is that in magnetic resonance imaging, the main tension or the main field strength, T's, on an MR machine is basically these tuners. But there are ways of changing the frequencies just a little bit, and that's through the use of gradient coils. And those gradient coils are somewhat analogous to what I'm doing here, bending a string either with my finger to change local conditions or using a whammy bar to change all the strings at the same time. So the parallel between tension in the equations that we just described, T on the guitar, and the Teslas, or the specification of an MR machine, 3T machine, 4T machine, 1.5T machine, that refers to the Teslas, and that refers to the magnetic field strength on MRI. And these are parallel concepts between the guitar and the MRI scanner. So let's go to the next variable, the string's linear density. And you can see that the top string here, which is called actually the sixth string, will sound a lower frequency because of its greater mass, or its linear density, which is the number of grams per centimeter of the string. You can see that a higher frequency is made by a thinner string because it has less mass and has more opportunity to move. So let's look at that. There's a range of frequencies that can be played as you switch the strings. In other words, there's a gradient of frequencies going from here to here. And that is due to the size of the strings. As you can see, the sixth string, which is this bigger string, has much greater mass than the tiny string here at the bottom, the first string, which has basically no windings on it and is very thin. What affects the frequency of the strings from the basic physics equations is the linear density of the string, the mass per unit length of a string. So obviously, a big string has a low frequency. A thin string is less weighty. It'll vibrate much faster for the same plucking, and you can hear that here. So we have a gradient from the large string to the thin string, an increase in frequency. And this one-dimensional gradient up and down is also used in magnetic resonance imaging, as we shall see later. So we develop gradients of frequency, and this is a good parallel with what I just described. So let's look at the final variable, changing the frequency of a string by changing its length. Now don't fret about it. I'm not about to go and get some cutters to snip the strings. But the length we're talking about is the vibrating portion of a string. So if you place your finger on a particular fret, only this portion is active and vibrating. The rest of it is basically inactive. As a point of interest, I wanted to point out, if you ever noticed, that the spacing of the frets on a guitar is logarithmic. And that is because a long time ago, when the guitar was being designed, it was thought to be best to change the frequency of the strings as we change frets in a way that has a constant percentage per fret. So you change the frequency, delta F over F, by 6% roughly per fret. And if you're going to maintain that, this is a logarithmic function, and that is why they're spaced that way. Another variable that affects frequency on a guitar string is the length of the string. And this might not seem intuitive, but you can change the length of a string interactively on the guitar. It would be very impractical if every time you played a different note, you had to reach out to some pliers and snippers and cut the string to the length of the note you want to play. So that's impractical. And the way that we do it practically is by using these metallic bars or frets. And these allow you to change the length, because if you play a string by holding on a fret position, for example here, only this portion of the string is vibrating. The rest of the string is now dead and does not come into play. So by changing these lengths, you can change the frequency of the sound. Let me illustrate that by going up the fretboard in this direction, and you will hear the frequency rise. And vice versa. So that's interesting. We now have a gradient of frequencies across the fretboard. We had a gradient of frequencies down the fretboard with the type of string and the density of string, and we have a gradient across the fretboard in accordance to the length that's vibrating in the string. So here's another relaxation point for you. get your mind off things before we wrap up part 1. Okay, it's time for another interlude to give you a break from all the equations and all the concepts and use the other side of your brain. So I'm going to play a tune, and again, I'd like you to name that tune. I'll just give you one hint, Roy Orbison. So here we go. So I'll give you a few moments to think about this. Second hint, Julia Roberts. Oh, you should know this by now. It was a movie. I think it was called Pretty Woman. And they used that as their introductory song. And it was composed by Roy Orbison back in the 1960s. And I hope you got this one right. And we'll move on to the next topic. If we change and play along different strings, and we play with fingers on different frets, we will generate this frequency gradient. And this is a two-dimensional frequency gradient going from a very low note, if we play the so-called open string by not pressing on this particular fret at the nut, the very low E note of a guitar, and climb all the way up to the usually the 16th or 17th fret, all the way up here in this corner of the guitar by pressing here with a finger. And you get a gradient both in this direction along the frets as well as along the strings, hence a two-dimensional gradient. I like to call the gradient along the strings the Y gradient, and I like to call the other along the frets as the X gradient. And that will come back when we discuss MR scanners. As we've already discovered, there is a large gradient of frequencies on the guitar according to the strings and according to the frets. What I'm going to try to do now is to illustrate the entire range of frequencies by playing the notes, by switching strings and switching frets, so that we reach the ultimate point back here, the highest note that you can play on this guitar. So here we go. There we go, the highest note. I've run out of frets. So that's quite a range and illustrates the two-dimensional gradient on the guitar. And similarly, on an MRI machine, we will explore two-dimensional frequency gradients. We have concluded part 1 of this lecture series, and to make sure that you've understood the concept, I would recommend that you try to answer the following questions. Maybe jot down the answers in terms of these questions here. What are sound waves? What are the main parts of an electric guitar? And so on. So you can pause the video here and jot this down, perhaps make this into an assignment if you wish. Now, we've covered a lot of guitar theory, but what does this have to do with an MRI scanner? This is former President Bush of the United States, and he's scratching his head on this as well. He also visited a guitar factory in the US, and he can play a little bit of guitar, but unfortunately his attempt at playing a G chord did not quite work out. He was off here by 1 fret. That's the way it goes. When you're president, you're busy, you have too much on your mind. So, we've covered the physics of the guitar. Stay tuned now. We're going to start in part 2 to describe the components of an MRI scanner and see how it parallels the guitar mechanics and the guitar electronics and the guitar concepts. I also wish to express my thanks to Dr. Donald McRobbie, who's written and edited as main author this excellent book From Picture to Proton, a book on MRI imaging. And in the book he does refer to the guitar as a a good parallel instrument to an MRI scanner. I think we both kind of co-discovered this at a different time, and I want to acknowledge his contribution to the understanding of MRI.